Good evening and welcome again. Today is May 18th, 2021. Thank you everyone for joining us today. I'm Phil Santonzi, Program Chair for ASQ Section 1510, Southeast Florida Section. Welcome to our monthly presentation. If you want to know more about ASQ Section 1510, please check our site at the Communities tab of the myasq.org website. And you can also join our LinkedIn group, ASQ Southeast Florida Section 1510. This live event is being recorded, as I mentioned, and we will upload this recording to our ASQ 1510 YouTube channel later. You will also be able, on the myasq.org website, there's a files repository, and that's one of the places, that's a place where you can find your RU certifications, the RU verification for attending this meeting. And it'll be there, again, at the myasq.org website at the Southeast Florida Section Communities tab and the files link. During the presentation, I ask that you please keep your audio muted until we open up for questions at the end. At this point, I would like to introduce Steve Kramer, who is the chair of the section and may have a few words. Steve, anything you want to pass along?
I just want to welcome everybody. It's great to see your faces. Feel free to please keep your webcams on as much as you can, just because it's great to see everyone. So even though you may not be the one talking, it's still nice to see you. So I miss all your faces and you may not miss mine, but that's okay. So I hope you enjoyed tonight's event and we look forward to you coming next time. And hey, we're almost out of this COVID nonsense. So we'll be back on the street, or I should say back into our face-to-face. But we will be still live streaming when we go back onto ground, because we want all of you who are remote within our region and outside of our region to feel welcome always. And we'll continue to record events. So whether you come to Tropical Acres or Shula's for our dinners, we will still live stream that and record. So hang with us.
Yeah. Hey, Phil, I've got one thing I just want to make before we go on with this, and that the latest variant came out just the other day. And within the variant, we have a survey for ASQ training. And we'd like you to go click on the link to go to that survey. And we're trying to find out your interest in which courses. But in addition, for each one of the courses, we show two options. We show an option for virtual, and we show an option for live. And we'd like you to give us your degree of interest in both the virtual versus the live, because we're trying to find out what people's interest level are. Okay, so if you're interested in the course and the manner in which you would prefer to see it, and the prices are there as well. Thanks.
Thank you, Bob. Thank you, Steve. Now to introduce our speaker and his presentation, Advanced Problem Solving, a Systematic Approach to Root Cause Analysis. Jim Leonard, who is the senior consultant with Quality Support Group. He's a consultant and educator who specializes in teaching the principles of the late Dr. W. Edwards Deming as a new system of management. Jim's clients come from a wide variety of industries and across sectors. He has worked with manufacturing and service organizations throughout North America, Europe, and in China. He's a senior consultant for Quality Support Group in Westford, Massachusetts, and has presented his seminars for the Division of Corporate and Professional Education at the Worcester Polytechnic Institute, where he also served as an adjunct instructor in graduate operations and industrial engineering. Jim is an alumnus of the U.S. Naval Academy, the George Washington University, and Clark University. He resides in Ave Maria, Florida, with his wife, Kate, and they are proud parents of 6 children and the grandparents of 10. Congratulations, Jim. His presentation tonight, Advanced Problem Solving, a Systematic Approach to Root Cause Analysis. For decades, management consultants, academicians, and practitioners have been searching for effective approaches to solving problems, ranging from major non-conformances in audits to small glitches in process and everything in between and more. Regardless of the problem scope, managers continue the search for a foolproof approach to problem solving. There are statistical approaches like SPC, design of experiments, which yield an understanding of problems and their causes in dynamic processes. But some question whether statistical methods effectively harness people's creativity and intuition when searching for solutions. Other methods like brainstorming, cause and effect, 5 whys have also been used with some success, but they sometimes do not capture systemic variation in root cause. Tonight, you'll hear Jim introduce a technique that connects a structured methodology for root cause analysis to a statistical understanding of the nature of work for more effective solutions to problems. Thank you, Jim. You have the floor.
All right, thank you, Phil. I'm glad you included the part of my wife, Kate, 48 years of marriage, 10 grandchildren, 6 children. That's all that matters. Forget the academic stuff.
That's right.
When you signed up, you had a chance to download this PDF executive summary that I originally drafted years ago for managers of the people who attend our systematic root cause analysis advanced problem solving workshops. It provides a pretty good summary of the concept as well as some attachments. So that's available. Also, Phil has asked, and I will provide him a PDF summary of the PowerPoint slides I'll be using tonight as well. I hope you find them useful. At any rate, when we're setting out to solve problems, we really have a choice. We can choose to focus our attention on problems with the quality of our products and services, or we can choose to focus on problems within or the quality of our processes that produce our products and services. As all of you know, we cannot do both. We've got to pick our poison. And at the risk of oversimplifying it, I always like to just use a little oil and pipe analogy. In this analogy, our product is our oil. If all goes well, it comes out, it's good. We can accept it. We can put it in a barrel. We can ship it and make money. Our process is, and I'll use the terms process and system interchangeably here, is the piping system through which the oil passes. And let's say for the sake of illustration, in one of your organizations, you choose to put your emphasis on the quality of your product. That's what you're focused on, is to make sure that product is good versus design specification, downstream customer needs, market demands, customer requirements. That's what we're focused on, is to make sure we have good product. A couple of weeks later, out in the middle of the desert, the pipe cracks. Dirt, sand, contaminants get into the oil. From our product quality focus, we achieve organization-wide consensus. We have a product quality problem, dirty oil. We cannot ship it. We cannot make money with it. From this product quality focus, you will ask, well, what corrective action will we take? And some people will say, well, fix the pipe. Remind them, Shana, we're not looking at the pipe, we're looking at the product. So what corrective action will we take? We'll slap on a filter. The filter serves to detect and screen out the contaminants. Now the oil's good again. We can put it in a barrel, we can ship it, we can make money. But please note, that filter in and of itself does nothing about our topic this evening. It does nothing about the root cause of the failures back up inside the pipeline. In the vocabulary of the systems perspective, that filter adds no value. All it does is get the oil back up to where it should have been all along, but it adds no value. What are some of the most common value-adding filters in Western management and manufacturing? Inspection and rework. I don't mean to offend any of you involved in tests, but you add no value, because that product's already good or bad by the time you test it. Rework adds no value. All it does is get the product back up to where it should have been all along when it first came out of the pipe. So again, in manufacturing, most often we call these filters inspection and rework, and our children's schools, we call them student testing and remediation. My grandson Will would say same difference, but it worked. For decades in Western management, this focus on product quality, this striving to become ever more efficient in AQL sampling, inspection, and rework worked, until we entered this new economic age and discovered on occasion the filter gets dirty. We weren't quite sure why or when. So we created QC people. And we told them, stand at the end of the pipe and look at the product as it comes out. If it's good, put it in the accept barrel, we'll ship it and make money. If it's bad, put it in the reject barrel, call maintenance and have them change the filter. And then we added redundant inspection and audit. Hi, I'm from corporate, I'm here to help you. Whose job it was to determine if that which we deemed clean was indeed clean, if that which we deemed dirty was indeed dirty, and if the filter was changed as scheduled. And one beauty of this emphasis on redundant inspection and audit that has evolved from this product quality, product problem focus on quality, one beauty of it is no one's responsible. That's the beauty of it. Those managing the pipe aren't responsible. The job of the inspector to catch it. After all, he or she has quality in their job title. I don't, I'm in operations. The inspector's not responsible. It's the job of the auditor to check it. The auditor's not responsible. It's the job of those working in the pipe to do it right in the first place. Right first time, every time, give me a t-shirt, it'll happen. And we end up with finger pointing, hate, blame, placing discontent, and excuses. And in our society, not work alone in our society. It's so much easier to engage in finger pointing, hate, blame, placing discontent, and excuses than to work on process improvement. And at the risk of oversimplifying it and all of its complexity, all Dr. Deming was getting at to his dying day, at the age of 93 in December 1993, he was asking us to sit in a room together, ponder on this slide for a nanosecond, and recognize all the value-adding resources we invest in this product quality focus on quality that add no value. All of our quality inspectors are value-adding resources. They could be out there on the line, making sure that work methods documentation is up to date and user-friendly, assisting supervisors in training new employees, assisting supervisors in upgrading the skills of experienced employees. But whenever we lock them in a mass inspection filter, they add no value. They're value-adding resources. But due to lack of knowledge, management deploys them in a fashion they add no value. And what Dr. Deming was saying was, management, learn your job and shift the emphasis. Develop the strategy, derive from that the annual plans. Within those annual plans, provide the training, the tools, the methodology, the direction that people might shift their emphasis from product quality to process quality. As soon as we do that, they see the crack. As soon as they see the crack, they patch the crack. As soon as they patch the crack, they will improve not only their process, but all of its future outputs. And we can, and forget the methodology for now. If we can take this concept back to work, share it with people, encourage them to strive continually to understand, maintain, and improve the quality of their process, 100% of the oil will be good. There'll be no need to filter it. Of course, we can't be out selling snake oil. This is not going to be overnight. Late 2000, a client emerged from 15 years of biomedical research in their labs outside London. And they decided it's time to go commercial. It's time to take this proprietary coating technology we've developed that mimics the hydration of the human cell and start to market it throughout the worldwide medical devices marketplace. And their strategy for making that painful transition from 15 years of biomedical research to commercialization was, we're going to implement a Six Sigma initiative. Six Sigma is going to be the methodology we employ. And I had the honor of working with their senior management team, their initial project teams, and their operations in England, Ireland, and Virginia. 12 months later, in their Norfolk, Virginia plant, 100% of the oil was not yet good. They had only gone from 65% first pass startup yields to 94% first pass yields. They still had a lot of work to do. This is not overnight. But what makes their progress most impressive to me, over the same period of time, they went from 2 cast molding lines to 9 cast molding lines, from 85 direct labor employees to 320 direct labor employees, from producing and shipping 200,000 compliant packaged units a month to producing and shipping 1.6 million compliant packaged units a month. So it's one thing to take these powerful methods and apply them in a pretty steady state operation to accomplish some gains. What makes their progress most impressive to me, they made this unquestioned progress. From 65% first pass yields to 94% first pass yields. Over the same period of time, they experienced a 4 to 8-fold expansion in production capacity, employment, and shipping levels, but 100% of their oil wasn't good yet. And what I always urge people in training and consulting, the challenge facing you is to take advantage of every opportunity you encounter to contribute to the strengthening of a healthy work environment throughout your organization, in which whenever you say the word problem or you say the word quality, you want this picture to pop into people's minds. This holistic model of pipe that physicist Walter Stewart came up with at Bell Laboratories in the 1920s. Intuitively, intellectually, those of you supporting production, they're going to say to you, well, this is obvious. Why'd you have to go to a webinar? We're going to have the best trained, hardest working people in the world in our manufacturing areas. If we get garbage raw materials in from a supplier, now who is that person who's dealing with the sourcing? Oh, Susan Green. If we get garbage raw materials in from that supplier, what's going to come out of our production pipe today? Garbage. It's so obvious. And yet, despite the intuitively obvious nature of this model, many of you may have months of work ahead of you to get this holistic model of the process that includes the product. It includes the product to pop into people's minds whenever you say the word problem, because we have been conditioned, we have experienced, we have been subjected to a completely different model. I like to call it the process model from the age of mythology, and there it is. Person equals output. And we need not go into the intermediate analytic statistical methods Walter Shewart developed, upon which he built his rational model. Just draw upon your own experience at work. Personalize this, your personal work careers. Beginning with your first part-time job in high school, have you ever had an immediate supervisor whose first question, when he or she has first encountered a problem, has been, who's responsible? Give me a name. If yes, welcome to the age of mythology. Have any of you ever worked in an organization? Several of you were talking about CAPA, corrective action, preventive action activities in your problem-solving approaches. Have you ever worked in an organization where a majority of their CAPA reports read, spoke to operator and told them to be more careful, or scheduled operator retraining? If yes, welcome to the age of mythology. Have any of you worked in an organization that has one of these sorry, self-esteem destroying, mediocrity inducing practices of annual appraisal of performance? If yes, welcome to the age of mythology. Because the fact is, folks, people can perform no better than your sorry process allows. Dr. Deming always stressed, you want to see better performance out of people, stop appraising them. Start leading them. Lead them back up inside your process pipe. Study the process, change the process, improve the process. Every time we improve a process, the performance of every person who works in that process can improve. In the absence of process improvement, people can perform no better than the process allows, no matter how many job-related bogeys and objectives we want to shoot out there for them for this review period. And at the output of any and every process, there will be variation. Dr. Deming taught and wrote variation. There will always be. Between people, between machines, between products, between vendors, there will always be variation. The key question, he insisted, the key question is, what is that variation we're finding at the output of the process trying to tell us about the process and about the people who work therein? He also referenced the Taguchi loss function, which is called the systems model of variation. It acts as a parabola. So he said, we need not achieve perfection. We need not achieve the precise optimum all the time, every time. A little bit of variation, one side or the other from optimum, any loss will be imperceptible. But the same model very clearly illustrates as variation increases, loss goes up, ultimately exponentially. We're scrapping an entire batch of production. So the bottom line of this Taguchi loss curve theory that I always stress people, this is what you have to share with people. Variation is the enemy because it's always going to introduce loss. It may be imperceptible, it may be staggering. The other way I urge you to share it, and I'm sure many of you do, our product is already good or bad by the time we test the product. The test adds no value. The enemy is the variation and sources of variation swirling in and around our development and manufacturing processes. From that insight, then we can derive some new definitions. Quality is no longer conformance. That's a recipe for mediocrity. How are you doing? It's meet and spec. Good enough. Oh, beware Six Sigma. What's the CPK? 1.33. Good enough. You've got to combat that inherent barrier to continuous improvement. If variation is the enemy, quality is minimal variation around some target or optimum value. That's quality. We have clients, they do not ship to spec, they ship to control. If they produce this unit today, they will not ship it. It meets customer spec, they will not ship it because it will introduce excessive variation to their customer's process. If variation is the enemy, how are we going to know that FMEA and DOE and root cause analysis and SBC and 5Y and 8D, how are we going to know that these are helping us make things better? How are we going to know that things are getting better? Reduced variation over time around some target or optimal value. There's improvement before and after. And we can now flesh out the key questions completely. And I'm not here to sell snake oil. Systematic root cause analysis does not get you here. FMEA does not get you here. DOE does not get you here. None of the methods we teach will get you here. Only leadership gets you here. To that healthy work environment in which individual employees and groups are continually without let up, seeking and taking action on answers to these questions. Question number one, who are my customers? Who uses what I produce? Who uses what I pass on? Question number two, what are their needs? Not their hopes and wishes. What are their needs? How can we best meet those needs showing minimal variation because variation is the enemy? And continuous improvement is measured by reduced variation over time because variation is the enemy. How are we doing? What can we do better? And guided by process thinking, we're always seeking and taking action on answer to the question, what can we do better in here, inside the pipe, inside the process? The tools we apply to continuously improve these, the tools we apply to continuously learn about these, the essential statistical methods. Basic tools. What makes a basic statistical method a basic statistical method? You don't need a calculator and you don't need software. Process maps. Fishbone diagrams, data collection, not statistical manipulation, just data collection. Pareto diagrams, run charts, histogram, basic tools. Another basic tool is systematic root cause analysis. But before we get into that, and it's for purposes of problem solving. The most common, I was keeping notes. I ended up we started out with a large group and then 2 breakout groups. By far, the most common problem solving tools that my breakout groups use, 5Y and fishbone diagrams. Guess what? Don't need a calculator. Don't need software. But before deploying them, we need operational definition. What is a problem? What is a problem? Charles Kepner and Benjamin Trigo noted that a problem can be defined as a deviation from what should be. The cause is unknown, and it's my job to do something about it. If these 3 factors are in play, you have a problem for which the topic of my presentation tonight was designed to be applied. Now, sometimes there's a deviation from what should be. It's a non-conformance, but the cause is known. That's not a problem. That's a corrective action issue. Schedule and take the corrective action to address the known cause. Sometimes there's a deviation from what should be. The cause is unknown, but it's not my job to do anything about it. Guess what? You don't have a problem. But when there is a deviation from what should be, the cause is unknown. It's my job to do something about it. That's our definition of a problem. And there are some pitfalls, some common pitfalls. I'm sure as quality professionals, you've observed them all. First, jumping to cause. Jumping to cause. We fall in love with a theory and we chase it down a rabbit hole. And in my experience, doing this 40 some years because my wife is old, in the vast majority of cases, this pitfall is self-imposed. Because we start to brainstorm possible causes of the problem so we can build our fishbone diagram, or we start to do 5Y before the problem's well defined. We fall in love with the theory, we chase it down a rabbit hole. Second common pitfall, failure to define the real problem. Marco Ferrao was making a point in the breakout group about the importance of data. Failure to define the real problem, difficulty therefore sorting out the really important facts, and the time pressure we're always under and we will forever be under. What's the most common pitfall that leads to? Jumping to action. We're get it done kind of guys. We got to move this from the inbox to the outbox and we got to move on. And what are the unhappy consequences? Far too many problem solvers suffer because of these pitfalls. I'll lump them into 2 general categories. You tell me, or you consider, do either one of these apply in my company? One, we'll call them people problems. Finger pointing, blame placing, communication breakdown, nobody ever listens, unhappy people. A second set, we'll call them productivity problems. The problems remain, the problems get worse, the problems recur. Somebody mentioned 8D. You ever gone into an 8D, your initial 8D meeting, and some wise guy has said, I thought we fixed that. Didn't you want to punch him? Who let this guy in this meeting? I thought we fixed that, and yet here it is again. The problem has recurred, therefore quality suffers, lost productivity, lost money. And we suggest that the root cause, peel back all the layers of the onions of these unhappy consequences. At the root cause of these unhappy consequences is the absence of a common, conscious, systematic approach to problem solving and root cause analysis. That's where we urge you to put your emphasis on the process, on the analytic process. It's a given in manufacturing. If I want high quality products, I must have a high quality manufacturing process. By the same token, if I have a high quality manufacturing process, I will produce high quality products. If I want to produce high quality solutions, I must have a high quality analytic process. This is where the automotive industry was coming from when they came up with 8D so long ago. They were tired of their vendors spitballing and they imposed this structure, this 8D structure that has grown over time and is now perceived by many as a time-sucking, inefficient, ineffective approach, the highly bureaucratic approach to problem solving. I mean, sometimes I'm in a meeting with a client and somebody says, well, let's do an AT. Boom, there's a rush to the door, run away, run away. You know, it's just perceived that way because of their negative experience. What we present, our systematic approach, 6 steps. 6 steps. Step 1, name the problem. This is a short, sweet, concise statement of the problem. Stay out of the weeds. What do we do in basic root cause analysis? After naming the problem, we brainstorm possible causes of the problem, or we do 5 why. Why. Guess what that leads to? Jump into cause. That's what that leads to. Not in systematic root cause analysis. Step 2, we're going to define and describe that problem in detail. We're going to construct, if you will, a detailed problem specification. Bucky Fuller, the inventor of buckyballs, molecular structures, long ago wrote that a problem well defined is a problem half solved. Here we are, only 2 steps into our 6-step procedure. We already have our problem half solved because a problem well defined is a problem half solved. Your next 8D investigation, do this at D2. Do not leave D2 until you do this. You got your problem half solved. Now it's time to list possible causes, brainstorming by the rules. But after the brainstorming, we do not transfer our brainstorming ideas to a cause and effect or a fishbone diagram. I don't care what your past training might have been in root cause analysis. We have not yet determined this is a process problem to which the multivariate fishbone diagram applies. No, what are we going to do? Step 4, we're going to test those possible causes against the facts noted in the problem specification. Does this theory of cause explain all of this? If yes, it remains on the list for further investigation. If no, we cross it off. We cross it off, sorry. I'm not pouring diagnostic time and energy into a theory of cause that doesn't meet my spec. I'm not doing it. I'm not putting it on a fishbone diagram. So in testing our possible causes, this leaves us step 5. We identify the most likely cause or causes. More than one may survive the test. If it's a process problem, more than one must survive the test. There is no such thing as a smoke and gun root cause singular to a process problem. It's always multivariate. So we've done all of this. Let's avoid that pitfall of jumping to action. One more step 6. One more step 6. Let's seek to verify in the quickest, cheapest, easiest manner possible. Let's see if we can either verify or refute whether or not this most likely cause is indeed the true cause. Once verified, we can move on to effective, lasting corrective action. And it is in that D2, that's the key. It's that step 2, describe the problem. We're very systematically describing our problem within 4 dimensions. First dimension, what is the problem or deviation we're trying to explain? Second dimension, where do we observe the deviation or defect? And this is in 2 respects. First, where geographically? Picture the process map. Picture the overview process map. Where are we observing this problem? Are we catching it in process? Final inspection? Did it make it out to the field? Is it in a customer's process? Did this show up in early new product development testing and we just didn't properly address it? Where geographically do we observe on the overview process map? But secondly, where applicable? Where on the object is the defect? Years ago, I was working with a company making psychotropic drugs for really whacked out people. And they had a problem. They were having seal failures on their capsules, and the drug was leaching out, and the people weren't getting sufficient proper dosage for their difficulties. So all they're just in the where dimension in their meeting, in their root cause analysis meeting. They put some of the failed capsules under the microscope. They discovered it was failing only at an isolated portion on the radius of the seal. It was not, as previously believed, a seal failure. This was a breakthrough in knowledge in describing and understanding the problem. But what it did was it knocked all the suspicion of epoxy, defective adhesive, out of the box. Because guess what? They were using adhesive all the way around that seal. If adhesive was the problem, why were they only observing that seal failure at an isolated portion of the radius of the seal? That came out of the where dimension. When? In 2 respects also. First, when did the deviation first occur? Right now, we're going to nail whether or not we're dealing with a day 1 deviation that has been around since product release. Or did it happen last week? Or was it first reported by a customer last month? When did it first occur? Secondly, since first observed, when is the problem occurring? pattern or trend. Now beware. Some of your people, they're going to hear pattern or trend, they're going to jump to size. It's increasing, it's decreasing, it's getting worse, it's getting better. No, we're in the when dimension. We're describing pattern or trend in terms of frequency of observation, using words like continuous, sporadic, intermittent, one time only. And the fourth dimension, size. How large, how serious, how extensive is this problem? And sometimes we're in our very first Kappa meeting. Those of you who brought up Kappa, you know what we decide? We're 30 minutes into it. No more work on this problem. Sorry, it's not a sufficient size and severity to be worthy of our limited time, limited people, limited resources. We've got bigger fish to fry. We'll slap a little D3 containment on this thing, but I'm sorry, it's not worthy of our limited resources right now. And we want to describe our problems within these four dimensions, not only what the situation is as observed, but also what it logically could be, but is not. We're following the lead here of Carl Jung, the late Swiss psychologist, who once wrote that it would be an expansion of knowledge to know what isn't affected. This leads us to another set of facts that is useful, but often ignored in describing a problem, namely the contrasting data. I want to just make a mention of the dimensions. Those of you who have done AD, I don't know if you're using the original rubric that the automotive industry came up with. The first dimension on their worksheet was who. Some of our clients are still using it because their customer requires it, medical device, automotive. I tell them, you take out a great big black marker and you cross out who. And when your customer asks them, why do you do that? Just educate them. Because when the first dimension you consider is who, guess what your corrective action is going to be? Spoke to operator and told to be more careful. We're setting out to fix blame, not to fix problem. No, we're not considering who. Another one on the original AT worksheet was why. Too soon. Too soon to consider theories of cause. Too soon to consider why. Great big black marker, cross that off. We're avoiding that pitfall of jumping to cause. But the way we describe our problems very systematically within these four dimensions, not only what the situation is as observed, what it logically could be but is not, is on attachment B of your executive summary. We pose and post responses to a series of controlled questions that we ask all the time, every time, word for word in sequence. And the first several times deploying these things, it's weird, it's forced, it's stilted. But it is a matter of time on task. You do get to the point that they start to become second nature. It starts to become a mindset. It starts to become the way you look at things. So 6-step root cause analysis. Step 1, name the problem, short, sweet, concise. It has both an object and an action. Bond failures on ABC circuits. Be specific, dealing with only one problem. Oh boy, quality professionals, warn your friends in production. Don't expect to make much progress with this technique with a problem statement of yield losses, high yield losses, high rejects, boil the ocean, solve world hunger while you're at it. No, you got yield losses, you got rejects. Go to your prior in-house data. What is the major defect type or failure mode contributing to your yield losses? Focus everyone on that major contributor like a laser, very specifically. We also want to make sure it names a problem for which the cause is unknown. Then, using the controlled questions, we describe the problem in detail within the dimensions of what, where, when, size, not only what the situation is, as I hope that's not that cat's opinion in my presentation, not only what the situation is as observed, but also what it logically could be, but is not. We then derive distinctions between the is and is not information. And then for any distinction we note the changes. And throughout this step 2, I want to go back to a point that a couple of people were making, but Marco raised it first, Marco Ferra. The importance of data. Throughout this step 2, you are Sergeant Joe Friday on Dragnet. Shana, you remember that TV show back in the 50s. Sergeant Joe Friday, he was a detective. He'd be investigating a crime. He'd be interviewing witnesses. And he would say, just the facts, ma'am. Just the facts, ma'am. When people started to go off on a tangent. Throughout this step 2, just the facts, ma'am. Just the facts, ma'am. No opinions welcome. No assumption allowed. No reading between the lines. No hypothesizing. Oh, this technique kills new product development engineers. They want to be hypothesizing. They want to be out in the stratosphere. That's what they do. That's what they're good at. But no, step 2, just the facts, ma'am. Just the facts, ma'am. Step 3, List possible causes, brainstorming by the rules, no restrictions whatsoever. All opinions welcome, all assumptions invited, all hypotheses encouraged. And then step 4, not a fishbone diagram. We test them against the facts noted in the problem specification. People will wonder, well, why are we bothering listing the is not information? Why don't we stay focused on what the problem is? Nitro, I worked with for decades, now purchased by Jabil, worldwide scientific injection molding. They're gray hairs. Any out of control or non-conformance situation, what was the go-to? Shrinkage, gotta be shrinkage. It's shrinkage. You got a 64 cavity mold, you got a 128 cavity mold, a lot of cooling and shrinkage has occurred by the time you get to that last part. I said it can't be shrinkage in the wear dimension. The out of control condition is on the X bar chart. The R chart is stable. It's not on the R chart. It's not doing this. It's not significant variability across cavities or subgroups. That would explain shrinkage. It's doing this. Shrinkage doesn't explain this. Significant batch to batch, incoming batch variation explains this. Tampering, human or automated, explains this, but shrinkage doesn't explain this. Walking out of that meeting, because we help facilitate, it's just a 2-hour meeting. The general manager looked up at me, she said, Jim, I can't tell you how much time and money you just saved me. I said, what are you talking about? She said, whenever this has come up in the past, my metrology lab technicians spend weeks of test and diagnostic efforts trying to verify the shrinkage theorem. She said, you pointed to one item on your flip chart page and it went away. I can't tell you how much money you saved me. I said, fine, I'll work on commission. But then after testing the possible causes, we identified the most likely cause or causes. If this is a process problem, more than one must survive. There is no silver bullet root cause, nor is there a silver bullet fix to a process problem. And then that step 6, pose, seek answers to good open questions. Let's seek to verify in the quickest, cheapest, easiest manner possible. Let's see if we can either verify or refute whether or not this most likely cause was indeed the true cause. So that's the systematic approach to root cause analysis. Dr. Deming, however, in one of his textbooks, it was very interesting. He spoke about the vice president of a huge concern who told Dr. Deming he had a very strict schedule of inspection of final product. Deming asked him, well, how do you use the inspection data? And the VP said, the data are in the computer. The computer has a precise, accurate description of every defect found. Our engineers never stop until they identify and address the cause of every defect reported in final inspection. Why was it, the vice president wondered, that the level of defective tubes in his plants had stayed relatively stable? 4.5% to 5.5% for 2 years. The same period of time, I might add, his engineers never stopped until they identified and addressed the cause of every defect reported in final inspection. Deming's answer, the engineers were confusing common causes with special causes. Every fault to them was a special cause to track down, discover, eliminate. They were trying to find the causes ups and downs in a stable system, making things worse, defeating their own purpose. So in this little paragraph, Deming reintroduces for your technical and management community some critical vocabulary terms: common causes, special causes, stable system, key ingredients of sound knowledge of theory of variation. It is not enough to be skilled in systematic root cause analysis, 5Y, 8D, fishbone diagrams, FMEA, DOE. It's not enough to be skilled. We must connect our skill with knowledge of theory of variation. In the face of one type of variation, systematic root cause analysis, steps 1 through 6, all the way through verification of true cause singular, works like a hot knife through butter. In the face of a different type of variation, apply steps 1 through 6 at your peril. I hope you have a lot of resources to waste, because you are going to join these engineers making things worse, defeating your own purpose. So let me just leverage off Deming's little paragraph here. Go back to the 20s and 30s, Deming and Shewart in the 20s, Deming's contribution in the 30s about 2 types of variation. They insisted if we agree that variation is the enemy, we must next seek to determine what type of variation are we up against. Shewart called it controlled variation. Deming called it common cause variation. This type of variation is random, mathematically predictable due to random chance. It's a result of common causes only of variation from within the process or system. So let's say we're going to take on deeper analysis of our data we collected in the when and size dimension in response to the controlled questions having to do with pattern or trend. And we determine that those evaluative data plot in a random pattern or trend. That's the key. We gain knowledge. This is the source of our problem. This is the cause of our problem. All of those outcomes, high and low, good and bad, conforming, non-conforming, all of them were produced by the same process. Therefore, our corrective strategy is and must be change the process. We form that cross-functional team that some of you mentioned in your breakout groups. We lead them up the pipe. They study the process. They must come up with recommendations, plural, for changes, plural, we can make to the process to solve that problem. We must have recommendations, plural. We must make changes, plural, because the problem is a result of common causes, plural. Again, we're evaluating the data we collected in response to some of the controlled questions in the when and size dimension about pattern or trend. And we discovered another type of variation. Stewart called it uncontrolled. Demi called it special cause. It's non-random. The evaluative data plot in a non-random pattern. We gain knowledge. It's not mathematically predictable. It is due to some assignable cause. Stewart said, Demi called special cause of variation from outside the process or system. So therefore, if we determine these evaluative data are a non-random pattern, we gain knowledge. Cause of the problem, some special cause from outside the process, and no amount of work on my process will address it. In the face of special cause variation, we take on a completely different corrective strategy. No fishbone diagrams, no DOE, no process FMEA, no multivariate approach. Name the problem, describe the problem. List possible causes, test possible causes, identify most likely cause singular, verify true cause singular, because we're out after a smoke and gun root special cause singular. And that's the theory, the knowledge of which must guide your Kappa teams. So what a problem, and I'm sure all of you share the same concern. My biggest concern, people are assigned to a Kappa project. They go in with the assumption there's a smoke and gun root cause of this problem. Guess what they end up doing? Tampering. They end up joining those engineers, confusing common causes and special causes and making things worse. And because of that, Dr. Deming insisted this knowledge is essential. Absent the ability to understand and differentiate between these two very different types of variation, we poise ourselves to commit very costly mistakes. And Dr. Deming documented 2 costly mistakes people will make if you don't assure yourselves that they understand these different types of variation. Deming's mistake 1, to treat as a special cause any problem, failure, breakdown, etc., that in fact was the result of common causes of variation. This results in tampering, not process improvement. Deming's mistake 2, to attribute to common causes of variation. In other words, to blame the process for a problem, failure, breakdown that in fact was a result of some special cause from outside the process. The process didn't do it. Classic example of Deming's mistake 2. Again, what is Deming's mistake 2? We are investing corrective action, time, energy, and resources into the process when the process didn't do it. Let's say in one of your manufacturing firms areas, your yield losses explode. You have not an increase in rejects. You have a significant increase in rejects. In fact, the special cause was a bum batch of highly, abnormally contaminated material going to one of your suppliers from one of their suppliers. But local management reacts to the defects as though our production process did it, and they invest capital in new machines and tooling. Local management just made a very costly mistake. Local management just flushed that capital investment right down the toilet because the special cause from the supplier to our supplier, if not identified, removed, and prevented in the future, will come screaming in without warning in the future, unpredictable by its very nature, and mess up those new machines just as readily as it did the old machines, and we flush that capital investment right down the toilet. And the order of waste due to Deming's mistake 2. Again, what is Deming's mistake 2? We're investing corrective action, time, energy, and resources into the process when the process didn't do it. The cause of the problem was a special cause from outside the process. The order of waste is on the order of billions, not millions, billions of dollars of misspent capital every year in the United States alone. Because America's business schools do not teach rational theory of variation. Deming's mistake 1. How do we help people wrap their brains around that one? Well, Let's say in a production machine or a test machine, we have a set point, time, temperature, pressure. But remember, variation, there will always be. Around that set point, there will be variation. Out comes a roving QA inspector, pulls a sample off the line, takes it back to the lab and tests it, doink. Hey, what are you doing? You're off set point. What does the operator do in this case? What has she been trained to do? What does the standard operating procedure, SOP, require the operator to do? Make an adjustment, get that thing centered. But in making that adjustment, they don't move just that one discrete sample the QA tech pulled. They will shift the entire distribution by that distance. Out comes a roving QA inspector an hour later, takes another sample off the line, takes it back to the lab and tests it, doink. Hey, what the heck are you doing? You're way off set point. What's the operator do? What has he been trained to do? What does the SOP require them to do? Make the adjustment. But in making the adjustment, they don't move just that one discrete sample the QA tech pulled. They shift the entire distribution by that distance. What has the operator done to the variation we started with? They've increased it. What do we do every time we increase variation? Increase waste, cost, loss. There are operators throughout a production system trying their best, making things worse. Because some engineer who lacked knowledge of theory of variation built that over control, tampering, variation, waste, cost, loss, increasing scheme into the SOP during process validation that the supervisors is using to train the operators. Now, let's go out of manufacturing. I'm not saying all, but many forecast and budget updates are tampering. Give me 30 minutes with your financial and marketing people and I'll prove it. Because we have a 3-month forecast. Yes or yes. Take a look at the end of the first month. Whatever happened there, we treat as an absolute and we we update. And then those operations people are out there playing badminton in a windstorm, not knowing what the heck they're going to have to ship next month. These are very costly mistakes, but now we encounter a dilemma. The human brain is incapable by eye or feel of looking at a data set, looking at a run chart, looking at a histogram, and determining by eye or feel, where is that line of demarcation that informs me whether or not my problem is the result of common causes of variation from within the process, in which case I pursue a particular path of corrective action, or is the result of some special cause of non-random goofy variation from outside the process or system, in which case I must direct or pursue a completely different course of corrective action. We need help. The statistician needs help. We need those practical statistics. And at the risk of oversimplifying it with time constraints, we go back to normal curve theory, where at approximately plus and minus 3, standard deviation measured from the average, we will find those lines of demarcation we cannot determine by eye or feel. Those lines of demarcation that inform us where the effects of common causes, plural, of variation and interactions between and among those common causes, plural, of variation leave off, and where the effect of some special cause of non-random goofy variation from outside the process may become evident. So many of our clients are finding it so difficult to apply this rational theory in their businesses because the normal curve is a static model. It just sits there. It doesn't even have a pulse. All of our clients work in dynamic processes. Things are never static. Things never sit still. Administrative banking, dynamic process. New product development, dynamic process. Manufacturing, dynamic process. How can this static model, however rational, how can this static model help us in our dynamic process world? Well, what did Walter Shewart do almost 100 years ago? When are all engineering schools going to get around to teaching SPC, please? I keep getting calls from Naval Academy. Hey, Alumni Association, would you like to make a donation for the turf field for the football team for practice? Are you teaching DOE and engineering yet? No? No. Click. Almost 100 years ago, he just flipped it on its side. He extended the upper and lower limits of controlled random common cause variation. He added the element of time. He invented the statistical process control chart that empowered him to plot key measures of his dynamic process outputs over time, real time. And he discovered if I observe a random pattern, that's the key, a random pattern cluster around the average or central line with no points falling outside the upper and lower limits of controlled random common cause variation. That's what those limits are. It has nothing to do with the control phase in DMAIC. Controlled random common cause variation. I gain knowledge. The source of this problem is common causes of variation from within my process. Therefore, and let's say this highest point here, it's a non-conforming product. If I am not pleased with that, he realized, I must change my process. Recommendations plural, changes plural. But he also wanted to be in position real time to know if he rolled his process dice and got a 13, something special happened. You know, I don't know about you guys. We've got some clients with their quality management systems. We have to lighten this up a little bit because statistics are boring to some people, not all of us. They will do a test and find a non-conforming product. Do you know what their protocol is? Test it again. I'm not making this up. They really do. They test it again. And you know, if there's enough variability in the test process, looks good. But you know what I always ask them? Well, do you test the good ones again? Never. I just make that observation. This happens sometimes because my wife's getting old. But that's the result of some special. He wanted to be on that evidence of special cause like a chicken on a June bug. Find it, remove it, prevent its reoccurrence. No amount of work on my process will address that non-conforming product. That non-conforming product was not produced by my process. It's a result of some special, he called it assignable cause from outside my process. So I hope we've hammered enough. The two of those key vocabulary terms Deming introduced in that little paragraph, reintroduced. Common causes, special causes. Now the other one, stable process. Stable process, what does it mean? It's in statistical control. Does that mean controlled variation? What does that mean? Random variation. What does that mean? All outcomes, though different, none significantly different. What does that mean? All outcomes, high and low, good and bad, in and out of spec, on time and late, all of them were the result of common causes only from within the process or system. Not pleased with one of them? Form that cross-functional team. Study the process, change the process, improve the process. Recommendations plural, changes plural. Because a stable process further informs us there is no special cause variation evident from outside the process or system. Was this tensile strength reading lower than all these other tensile strength readings and tests? Yes, and everybody can see it was lower. Maybe it was out of spec, but it was not significantly lower. Did this student score higher on the math exam than this student? Yes, anybody can see that. He or she scored higher, but he or she did not score significantly higher. Not happy with low test scores? Get back up inside the teaching and learning process pipe that generated that low test score. Study the process, change the process, improve the process. Issuing a low grade to this child does nothing to improve the process and produce that low test score. Issuing a low grade to this child destroys the child. It destroys the child. Our teachers are wielding that power without mercy because they wield it without knowledge, because they do not teach rational theory of variation in the School of Education any more than they do the School of Business, any more than they do most schools of engineering. When are we going to wake up? I'm a little tired of spending my career doing rework. Teaching those powerful techniques to people who should have come out of engineering school knowing them as readily as we know the conjunction and. See, you get to 70, you get cranky. So where does this take us? Let's go back to where we started. Kepner and Trigo. Oh, it's a problem is a deviation from what should be. The cause is unknown. It's my job to do something about it. Let's connect knowledge of theory. From now on, for purposes of systematic root cause analysis, steps 1 through 6, all the way through verification of true cause singular, our definition of problem is a significant deviation from what should be. The problem is not, are these outcomes different? The question is, are they significantly different? If they're significantly different, then we know there's special cause. And we do systematic root cause analysis, steps 1 through 6, and we can avoid all those costly mistakes that too many problem solvers are making. So in your executive summary, you'll see this little advanced problem solving process flow. I'm just going to, it's provided in the handout, but I'm just going to touch on a few of them. Well, first, we plot our key measures on a control chart. Is the process stable? If yes, work to improve the process via cross-functional teams, process FMEA, design of experiments, multivariate techniques. If the process is not stable, or if for whatever reason it's not applicable, maybe you're not using control charts in new product development. I hope you're not using control charts in new product development. If your new product development projects are taking so long that a control chart's applicable, you got a problem. Now, we use them in our test labs with those repeatability studies, because man, those development engineers have to be able to trust those tests. They are making product release decisions on very limited data. Oh man, yeah, we're using control charts in the test lab. but not in new product development. So, if the process is not stable, or for whatever reason that question may not be applicable, now we proceed. We name the problem, short, sweet, concise. We put on our fedoras. We're Sergeant Joe Friday, just the facts, ma'am, just the facts, ma'am. We describe the problem very systematically within the dimensions of what, where, when, and size, what the situation is as observed, what it logically could be, but is not. Once with the is and is not information, we note any distinctions between the is and is not information. X bar chart, R chart, for example, in NIPRO, one plots variability of the average, one plots variability of the range or dispersion. And then we note any changes in or about each distinction. These 3 steps: draft problem specification, note distinctions, and note changes. Just the facts, ma'am, just the facts, ma'am. But next, list possible causes. Brainstorming by the rules, no restrictions, and test them against the problems, the facts noted in the problem specification. Now, has anyone heard me? You might have to unmute and let me know. Has anyone heard me say that I cannot apply systematic root cause analysis to a stable process, because if I do, I'll end up making a costly mistake and tampering?
Yes.
You heard that, Phil? Enough. Okay. I cannot apply systematic root cause analysis steps 1 through 6 to a stable process, or I'll end up tampering if I think I can verify a true cause singular. Let's say I've got a control chart in my hand. This process is stable. It's in statistical control. Or let's say in the absence of a control chart, we're in new product development or marketing. People are describing patterns or trends with words like continuous, steady, consistent, repeated. That's a real strong indicator. This is a common cause systemic issue. Not 100% confidence level in the absence of a control chart, but come on, give some credit to your investigators. In that case, I can benefit from systematic root cause analysis. I will go to step 4 and no further. And what do I end up with? An unprecedented level of detailed definition and understanding of my problem, and a way to very efficiently test and reduce my list of possible causes. Not to one, but maybe I'll go from 25 suspects to 10. I mean, I was working with a client out in Detroit that they made sound systems, automotive, new model year. And they were dealing with a problem with technology transfer and scale up. Nothing new, nothing special. They got to do it every year. They had already identified 32 variables for their DOE. Their corporate statistician was back at headquarters laying out the matrix for. I'm thinking he must have a cray computer. They're going to juggle 32 factors. This is going to kill me. In our workshop, the final exam is they actually apply all of this to a real problem. So they did it to that transfer and scale up problem. We walked out of that room with an 8-run Plackett-Berman screening design in our hand to test the 7 surviving factors. I'm not making this up. Literally 25 of their 32 suspects failed to explain something when we had it documented in this fashion. In the fashion, we won't go into it, but in the fashion of another problem that's noted on the back of your executive summary of an actual worksheet that we put together in a couple of hours with a client in Indianapolis. But in this case, going from a god-awful 32 factor experiment to a highly efficient 8-run Plackett-Berman with 7 survivors. I work with engineers. They will sit at their desks all by themselves and do systematic root cause analysis up to this far to select factors for their DOEs, because they don't want to waste experimental time and resources on factors that don't meet the spec. So, am I dealing with common cause variation, control chart, stable control chart, or people describing patterns or trends with consistent, continuous, steady, repeated? If yes, stop here and go no further. On the other hand, I do have a control chart in hand. The process is out of control, or in the absence of a control chart, knowledgeable investigators are describing patterns or trends with words like sudden, sporadic, intermittent, increasing, decreasing, not seen before, one time only. That's a real strong indicator it's a special cause situation. Not 100% confidence level in the absence of control chart, but give your investigators credit. In that case, I will proceed. In testing my possible causes against a problem specification, I'll identify the most likely cause. One more step, verify true cause, fix the problem, and then extend the fix. Think beyond the fix. This is like D7 and 8D. Think beyond the fix. You know, might the verified cause of this problem be causing other problems? Maybe I just go to corrective action without having to reinvent the wheel. Or let's stair step the cause. What caused the cause? What caused the cause? That will lead us back up into the process, and we start to get involved in process improvement. So I'm not sure where I am. I hope you know. Okay, that's kind of what I wanted to cover. Questions, comments, curses?
Thanks, Jim. Anybody have questions for Jim?
I don't have question, but I just want to say that I use the AD problem solving approach because it's very similar to what you explained here.
Yep.
Add the two more steps, which is applied to a preventive step to apply the same results from your the true cause into similar products, family of products, and then the A1 is to congratulate the team.
Okay.
So basically the idea.
Yeah.
And the other thing
Well,
is that,
you know, Marco, you mentioned 8D. I promise you, your next 8D investigation will go more smoothly, more efficiently, and more effectively than your previous one. I promise you this if you do this. The key is D2.
yeah,
Name the problem,
yeah.
describe the problem, construct
You
that
have
problem
to use
specification.
the four W's and one H. I mean, that's
Oh, don't give me the
basically-
4 W's and 1 E's. Pay attention to the handout. It's got the controlled question. 4 W's and 1. Don't make me hurt you. But then D3, we can take effective interim containment because we know what we're containing.
Yeah,
We
well,
really
containment-
understand the problem. But as you know,
Containment-
there has to be the personal and organizational self-discipline to push beyond D3. D3 does not solve a problem. It just stems the bleeding. Next key, D4, list possible causes, test them against the facts noted in the problem specification. In doing so, we identify most likely cause, verify true cause. Do this. I urge all of you, do this. D2, D4, in your next 8D investigation, I promise you, D5, 6, 7, and 8 will flow more smoothly, efficiently, and effectively than your previous investigation. Don't do this in D4 and D2. That's why everybody hates 8D. Because you get bogged down
you need
forever.
to do D3 to avoid immediately to pass product that have that is effective. You have to actually do that immediately. But then you go to identify the true problem.
Yeah, but
And then you
remember,
apply
D3, all you're doing, you're increasing inspection, you're setting up a quarantine
Well, you have to
area.
do. If you don't do it, what is going to happen? You're going to be shipping bad product. You have
Sure.
to. You have to start sorting out from the stock room and everything with whatever product is bad there. Otherwise, you're going to have a problem. You have to do a containment all
That's
throughout
right. That's
the
a-
manufacturing process.
That's a problem when you're really good at containment. Nobody sees a problem anymore. And 6 months later, you still have the increased inspection. You still have the quarantine area.
Yeah,
The
and
problem is
unfortunately,
itself.
that happened. That's a real world. I mean, I work in the aerospace industry. It's a discrete manufacturing, low volume, and it's very difficult to apply control charts because
Yeah.
you need more volume of that. I have used P charts a lot
Yeah.
because it helped me. If it's after the fact, the P chart, but still, it helps you to identify somehow and reduce all the, I mean, start looking at the variation, whether when you have a P chart, the P bar is going to start going down until you're going to have only one upper control limit, basically. I mean, it disappears because if you have a high volume, you're going to have two control limits, upper and lower limits. And
Yep.
as you reduce the number of defects, the lower bar is going to come down. The P bar is going to come down, and you're going to have a symmetric type of until you're going to disappear everything. So in aerospace, it's a problem with that because you have to have it's a discrete low volume one. It's very
Right.
difficult to use. The only
And in that case, as I mentioned, Marco, new product development, capital equipment, pay attention to the words people are using to describe patterns or trends. Trust your investigators. Continuous, steady,
Okay,
repeated, common cause.
Yeah.
Sporadic, intermittent,
Okay.
isolated, not seen before, something new.
The worst thing is to try to resolve a common cause. I mean, it's inherent to the process. inherent to the, you cannot do that. The only way to do that is to present it to management, since that's what we have. Either you change completely to a different type of process, or you have to live with the problem.
Yeah.
I have done that in the past. That's the only solution when you have that.
Yeah, and the beauty of this technique, you have the problem so well documented. You're able to give, you've done your job. You're able to give management the information they need to make that call. They get paid the big bucks. Okay, we continue. I'll give you resources to fix it, or we get the heck out of the business. I mean, that's basically the three choices. But man, with this approach, you're really giving them detail.
Just one thing that I want to tell you, the D3 is just temporary until you are able to come with a permanent solution.
Yeah.
And also, at the meantime, you also do some type of, if you're having problems in the store, that means that your supplier is doing something wrong, you communicate to your supplier. So you're going to start stopping, they're going to start from sending you wrong bad product. You understand what I'm saying?
Yeah.
And also you start identifying internally in order to avoid to ship bad products to your customer.
Yep.
You have to do it, but it has to be temporary.
Okay, thanks, Marco.
Yeah.
Jim, I've got another question here about, let's see, when it comes to consumer products, like at a bank, IT products or apps, what steps do you advise for use? Apparently Adelaide, who asked the question, hasn't really seen any of this in her current current meetings for problem solving.
I would encourage her to read over the executive summary and just start asking some, perhaps not all, but some of the control questions. What specific item, object, unit has the defect? For example, I've got a report that's got a large discrepancy between two auditors. Well, what one is that? But then he is not. What similar report could logically have that same defect but does not? I mean, that's going to be so rich when she's thinking, okay, this one's working, but this one wasn't. What is it about that? What specifically is the defect? What other defects could logically exist, but they don't? And this also makes you very efficient in testing your theories of causes. No, that can't be the cause, because if that was the cause, we would have had the same problem with the other report, and we didn't. And it gives her a way to sort through and challenge once the problem's well defined in an administrative setting, any theories of causes.
Okay.
So I would recommend starting with the questions.
There's a question about your diagram, the process diagram with the 3 M's, the P, and measurement. Is why do you describe that with measurement at the front end, near the fish head, so to speak, instead of as a leg?
That's where everything's coming out. Measurement is a part of the process, but all of those effects of the other 4, or you can always add a 5th, it's coming through measurement. Measurement is always a source of variation, waste, cost, loss. Always. They could be in there measuring with the precision of a yardstick when I need the precision of a plug gauge. So it doesn't matter how perfect my materials are, doesn't matter how perfect my methods are. It doesn't matter how highly calibrated my machines might be, how highly trained my operators might be, my people might be. Measurement can be a source of variation. I just do it the way Stewart did it. I don't know why people changed it.
I like it a lot when you superimpose the fishbone diagram to the control chart, because basically the fishbone diagram actually partition the variations. People don't understand that.
Yeah, that's not the fishbone diagram.
They don't know what they're doing.
Yeah, I don't want to mislead you. That's not the fishbone diagram. That's the process.
No, there is one that looks like a fishbone diagram.
Well,
right.
That's because Ishikawa made the fishbone diagram look like the process model.
Yeah, okay, well.
If I guess if I would with just one thing, and I know I'm not telling anything to the vast majority of you, the frustration I suffer, and I know you do, when you see a team setting off to address a problem, assuming there's going to be a smoke and gun root cause. I mean, they're setting themselves up to join those engineers Deming wrote about. And with your professional guidance and maybe posing some very powerful controlled questions, you can keep them on track and protect them. So thank you. Thank you. God bless you. My email address is here on the final slide. If questions, or if you're thinking about this, questions arise, problems are encountered, please don't hesitate to contact me. I'll be happy to get back in touch. And the quality support group website, we do a lot of quality systems and auditing and things like that out of headquarters, but all over the world, is just qualitysupportgroup.com. So thank you.
Well, Jim, I want to, we appreciate your being here tonight and giving us this this great presentation. We do appreciate it and thank you very much.